Okay, so today we will construct a square with the same area as a rectangle using the mean proportional. So first of all, we are going to extend this line AC. So if we just extend this line out here, we're now going to take the height of the rectangle and we're going to swing it up onto this new line. We're going to label this as point D. Now we can fill in the rest of our line AD. Next of all, we want to get the midpoint of the line AD, so I'm going to get my compass, place it on D, I'm going to get a distance more than halfway, swing above and below. Now the same distance from the other side of the rectangle, swing above, swing below. I can join these 2 points, join here and here. This is now giving us the midpoint of the line AD. So now we can draw in a semicircle here. So we draw our semicircle. Now we have a semicircle which goes from A to D. So next of all, if we draw a point from C up as far as the edge of the semicircle which we have just drawn, this is our mean proportional. But the most important part of the semicircle are the triangles which are hidden inside. If you now draw in these triangles, so if we join from the edge of the semicircle to here, now draw on the other side, if we join from D up to here. Now, as this vertex hits the semicircle, we know that a vertex hitting the semicircle gives an angle of 90 degrees. In a triangle, so there we have an angle of 90 degrees there. As this is a straight angle, we know we have 2 angles of 90 degrees here. Now, to make it easier to prove that the triangle is similar, I'm going to sub in some angles. So if I sub in an angle of 60 degrees here, this will mean that up here we have an angle of 30 degrees, as there are 180 degrees in a triangle. This will then leave us with 60 degrees here again, as that is a right angle, and we will be left with 30 degrees of an angle down here in the bottom left hand corner. Now as we have one side of our square, we can draw the rest of it. So if I take the length of this side, if I swing it over here, now construct a perpendicular up here. Now if I take this distance again, and I swing it over onto this perpendicular which I've just constructed, I now have my square. So now we've constructed our square. We'll just heavy in the square here. Okay, so there's our square heavied in. So now we want to prove that these 2 triangles are similar. So what I'm going to do is take them out and I'm going to separate them. If I change the orientation, it might make us easier just to visualize them. So now, if we look at these angles, we can see that angle ACB, which is here, is equal to angle BCD, as both are 90 degrees. If we look at angle BAC, we know that it is equal to angle DBC, as both of these are 30 degrees. And if we look at our final angle ABC, we can see that it is equal to the angle BDC, as both of these are 60 degrees. Now if we want to label this point up here, B, if we want to find the altitude, BC, we look at the ratios of these triangles. So if we look down here, we can see that the ratio DC is equal to the ratio BC of the bigger triangle. If we now look at BC in the smaller triangle, we can see that this is equal to the ratio of AC. So if we want to put these ratios over each other and make a fraction, we get DC over BC, which is equal to BC over AC. Now if we cross multiply these ratios, we'll come out with the formula BC squared is equal to AC multiplied by DC. As we know, BC is a side in our square, so if we have BC squared, then this will give us the area of our square. And as we can see, BC squared is equal to AC multiplied by DC. We know that AC is one side of the rectangle, and we know that DC, which we have swung up here, is the other side of the rectangle. And AC multiplied by DC will give us the area of the rectangle. So as we can see again, we have just proven that BC squared, which is the area of the square, so the square is equal to AC multiplied by DC, which is the area of the rectangle. We've now proven that the area of the square is equal to the area of the rectangle using the mean proportional.